Okay, so Flywire, is a whole fly brain connectome. For anyone who's not familiar with it, we had a special edition with a package of papers that came out in Nature in October of last year, and research and investigations into the fly brain is exciting and ongoing. Um, we have now partnered up with Wei-Cheng Li's lab at Harvard Medical School to have a new data set available within Flywire. So the sort of like bluish purple one, FAFB, is the original Flywire brain. And we've now been proofreading in the bank, the brain and nerve cord. For a comparison of the expansion that the bank offers to Flywire, you can see the whole VNC, the whole central nervous system, considerable more uh, nervous system tissue in there. And we recently completed proofreading the 100,000th neuron in the bank. Here's a little snapshot of, I think, around 1,000 of them. This is cells that were proofread mostly by citizen scientist Nesterov. Nick, I think you're here, so I was excited to share a little video of some of the neurons that you did. It's amazing to see where these neurons go after they exit the brain. And, of course, it's not just proofreading, it is also annotation that's happening in the bank. If I can get out of this slide. There we go. So Jasper provided this update. There's 154,000 entries in the bank soma tables. So far we've proofread about 2/3 of those cells. And they have about 44,000 of those cells have been typed. And thanks to Ari, they are available in Codex. But I do want to mention that you have to have early access to bank in order to unlock this zone of Codex. So you can go to this URL and request early access if you want to see the annotations and the proofreading, and also please to contribute to the annotations. Alex and Rari put together and shared these draft figures. We're still in the preprint phase. It's very much an early release of the bank. But this just gives a snapshot of where the proofreading has been most concentrated, where there's more to go. You can see, still 60% of the cells in the optic lobe have not been proofread. And a lot of those cells are smaller, so maybe that can go faster. And you can also see a status of the manual inter-data set matching, not purely manual, but I think each one of these that is determined to be matched has been looked at by a person. So the neck and VNC are coming along quite nicely, but still 64.7% of the neurons in the central brain have yet to be typed. So please contribute annotations to the bank so that this data set can be as robust and well annotated as possible whenever the preprint comes out. So I think that's all I put. Yes, Ari, I'm going to pass it off to you. I don't know if there was anything else I was supposed to cover, but.
Thank you, Amy.
All right, thank you.
All right, so okay. Hi, everyone. Welcome to Princeton. Welcome, everyone online.
You should probably talk into them.
Yeah, I should probably stay here. Thanks for joining our session. It's great to see all the participants together with our labs at Princeton and other colleagues. We will start with a quick reminder of the data challenge. So what we've asked to do in this challenge came out in October, and our goal was to match neurons from the MANC dataset. It's a dataset of a nerve cord of a male Drosophila, and our own bank, the dataset that Amy just mentioned. And we wanted to have an alignment of the neurons from the two nerve cords of these two different data sets. And there are several ways to do this kind of alignments. And the one that we're interested in was based on connectivity alone. And so we phrased this challenge as a kind of a graph matching problem. where you have two directed graphs and you want to sort their adjacency matrices so that if you align them under some objective, you can calculate your score, and then the winner is the one with the highest score. And we use these types of alignments for a few kind of goals in connectomics. One is to compare connectomes, to carry over annotations. For instance, in this case, MANCI is a fully annotated data set, and we can accelerate annotation of the BANC data set if we had the exact mapping from the neurons in one data set to another. In this case, it's also different genders, male versus female, and this kind of alignment is useful also to identify which types of neurons are different between males and females, or which types of neurons are only in male or only in female. So this was the challenge, and we had 13 teams and 31 participants. So first of all, thank you all for participating, for your hard work and enthusiasm. I do hope it was a fun challenge, and you enjoyed the diving into the data and trying to optimize the scores. We have, I think, 4 or 5 teams present here, which is also very exciting. And we'll hear presentations first from the winning team, but then in the next session we'll hear presentations from other top teams in a little bit more detail. So with that, somehow it came to a state where the winners were kept in secret, and now we're going to announce the winners, the team Old School. This is how AI imagines team Old School solving data challenges. And I think they didn't use punch cards, but otherwise. But still, the solution is very efficient. So maybe it would even work with punch cards. So very exciting, and drum rolls. Congratulations to Daniel and Lawrence here in the first row. Maybe before you start your presentation, we have a little gift. Very special.
Are you used to?
Thank you. Thank you. Thank you. Please, take away. Stage is yours.
Yeah. Place the. Okay. All right. Okay, everyone can see online and hear us online? Oh? Yep. All right. Great. Oh, we should do a slideshow. Yeah, slide. Still. Okay, great. Okay, so we are Team Old School. Thanks for having us here today. What we'll talk about today is our title is Hard Swaps and Soft Relaxations for the Flywire Graph Matching Challenge. There's a number of reasons why we called ourselves Team Old School. First and foremost is that we have graying hair, but we actually go back a long ways together. We actually were college students together and grad school students, PhD students together. We actually trained in physics. So that's kind of an old school discipline. But, as physicists, we wanted to apply some of these techniques to new problems. And one of the interesting things is to try to use some physics intuition, these kinds of methods, to try to solve problems that seemingly seem difficult. So that's kind of what we're hoping to give you a flavor in terms of what our approach was to this challenge today. Okay. Yeah, as again, thanks to the organizers. Just to remind you about the challenge was the ventral nerve cord, 18,000 neurons to find a permutation matrix there that would kind of align graphs together. So what we wanted to do is kind of introduce, how we thought about this problem. So, at a high level, what we have is we have two connectomes, two graphs. One described by a matrix A, which is the adjacency matrix for counting the number of synapses from node I to J in graph A. And we have another graph described by a matrix B. And what we're trying to search for is a permutation that takes, 18,000 neurons, matches them to 18,000 neurons in the B connectome. And we have this alignment score, which is to, maximize the sum over, all the minimum of these synapses that are aligned together. Okay, so that's, was the challenge. Let's see. And so what we wanted to do today was kind of in terms of the sections of our talk, I'm going to introduce basically a simple recipe to get to a winning score that takes about an hour on a laptop in MATLAB. So just to show you kind of how some of these simple ideas can work in this problem. And then Lawrence will tell you kind of some of the more interesting things that we went through during this challenge to try to make sure that we completely optimize this score. All right. So the first part here is to think about this problem, and the way we approached it is to think, you want to find a good permutation matrix, but you can do these relaxations. And so one simple relaxation or permutation matrix is a set of kind of sparse doubly stochastic matrices. And then you can then go to dense doubly stochastic, the full set of doubly stochastic matrices. And, the permutation matrices are just a subset of these, and they're the ones that are actually orthogonal. Right. And so what we wanted to do was think about methods that operated not only in permutation matrix spaces, but also in these kind of sparse doubly stochastic as well as full doubly stochastic matrix domains. Right. So just to remind you, right, we have actually this objective function that's this basically a quadratic function on the entries of these permutation matrices or the doubly stochastic matrices. One thing to point out is that this is actually a non-convex objective function that was for this challenge. So even if you're working in a relaxed space, it's still a non-convex problem, which makes it hard. And so, all our techniques were basically kind of first order techniques here, which means that you calculate the gradient of this objective function, which you can then write down in the following way, right, in terms of the matrix P. All right. Some things to point out is that this gradient is also non-negative, and when P and A and B are sparse, it's order n squared to compute this. But then once you get to dense matrices, it's going to become order n to the fourth. So the kind of naive way of calculating a gradient with a dense matrix is actually very tough to scale in this problem. All right.
Question?
Yep.
Do the matrices have to be square in this algorithm?
In this one, yes, because A is basically just mapping, this basically adjacency matrix, so it's a square matrix.
Extended to non-square matrices?
We have methods of thinking about doing that might be a future talk. So, all right. So some of the kind of basic operations that you want to do is if you're given kind of a doubly stochastic matrix to find basically the closest matching permutation matrix that is basically a linear program. It's known as the Hungarian algorithm that can do this pretty efficiently, so that given any kind of a Q matrix here, you can find the nearest matching permutation matrix P. The other one is then to basically maximize over this linear objective. So it's, again, a linear cost function. If you do this to find then the permutation matrix that will actually give you the best linear match there, okay, with the linear objective. So these algorithms typically are order n cubed, but we have methods to actually do some preconditioning that can kind of speed these things up as well. All right. Okay, so in terms of then the actual optimizations, we had a couple different ways of approaching this problem. One is kind of a traditional additive update, which is you would take your initial P matrix, you calculate the gradient, you then project that gradient onto the best permutation matrix, and then you then do some sort of line search additive update. You search along that additive direction to optimize the matrix P. This is something called the Frank-Wolf algorithm. It's a very well-known algorithm for this type of approach. The other approach that we had is something more old school. It's a multiplicative update, which takes the matrix P and multiplies it with a non-negative gradient, and then basically is able to normalize that. This has actually connections to our old work, actually on non-negative matrices and stochastic matrices. It's related to something called the EM algorithm. And the way you can show that this type of multiplicative updates are guaranteed to kind of do, to continuously improve the score function is using these variational methods that Lawrence has been an expert on. Okay, and then what you want to then do is once you are, say, have a good doubly stochastic matrix, then you can project back down to the permutation matrices. All right, so these are some of the basic operations. And then another one is to do pairwise swap. So this operates only in permutation matrix. So given a permutation matrix, you can basically look at finding pairs of nodes to swap in the permutation matrix, which then hopefully which will improve the score. And this is just a snippet of MATLAB code that's actually 10 lines long that can actually do this efficiently in MATLAB.
Just a quick question on the previous slide.
Mm-hmm.
So in the multiplicative update, you're adjusting UI and VG to have those double stochastic.
Yes.
And then the first line of that is also going to be double stochastic.
Yes. Yes. It'll mix whatever starting matrix with a permutation matrix along a line, so it'll still be in double stochastic.
But the delta has to be double stochastic or a permutation.
Permutation matrix with Frank-Wolf. Yeah. So a convex combination of a doubly stochastic, any two doubly stochastic matrices will be doubly stochastic. And so a permutation matrix is an example of a doubly stochastic. Okay. Okay, so if you do this, this is kind of a recipe that you can use. This is, say, starting from the benchmark permutation matrix. You can run, Frank-Wolf here for a number of iterations for, in our case, about 30-some minutes. You can then follow that up with these sparse multiplicative updates to further improve from the Frank-Wolf solution. You then project down to a permutation matrix, and then you do pairwise swapping in that permutation matrix, which will get to, in 1 hour on a laptop, we'll get to a score of 5,851,000, which was our score back in December 21st in our submission, and that would have won the competition.
Sorry, the projection is rounding, or is this the
Hungarian algorithm on the doubly stochastic matrix.
And you have some freedom there as well, right?
You can play, we were playing around with different ways of trying to do the projection, maybe not using Euclidean norm, but other types of norms and things like that.
So the Frank-Wolf seems, where does it max out? I guess it's a little bit.
Yeah, so it gets up to some, here it's, with the doubly stochastic matrix, you'll see that we're getting scores of 5.8, 5.3, something like 4 or 5, something like that. And then when you project, it's actually much worse on the permutation matrix, and then we improve that with the pairwise swap.
Okay, so you have to project that out.
That's what this discrepancy is.
To the nearest permutations?
Yeah.
Okay.
Yeah.
So
That's cool.
If you take out the green part, is that FAQ?
The green part,
yeah,
that's largely.
Well, yeah, the difference is that they're using a nonlinear. We'll talk, and we're just using a quadratic function. We weren't clever enough to take the gradient through the min. We were saying,
right.
FAQ is the quadratic function.
Yes,
That's
right. And I'll show how what we did there and the gyrations.
But
and
super
standing
close.
on one foot and touching on. Thank you. This is great.
All right. Okay. So next, then Lawrence will describe further improvements.
So I will, in some problems, they say the last 10% takes 90% of the time. So in this problem, it's really the last 0.01% takes something like 99.9% of the time. So I'll talk a little bit how we do that. I already said that our goal was to reveal, our secret sauce. So let me just say our secret sauce is this person standing next to me for the most part. But let me talk about the things that got us to our highest score. All right. So the first thing I want to point out, this is showing like the first graph Dan showed was 1 hour to get to roughly 5.851 K. To get the next couple thousand, the hours go up quite a bit. And now, instead of spending most of your time searching in the interior of the simplex, over doubly stochastic matrices, you're spending much more of your time searching through permutation matrices, right? So just in these 8 hours, I think in the last slide, it was like 90% of doubly stochastic. And here you see that we're down to 25% of our time spent in doubly stochastic. Everything that Dan talked about so far was just stuff done on laptops. For some of the searching through doubly stochastic matrices in the last part of our efforts, we did put some things on a GPU, okay? But still, it's a relatively small amount of the effort. Most of the work was just done on laptops and a CPU. All right, so I'll try to make sense of our extensions. It was a kind of a crazy effort, but you've heard about 3 different types of moves that we did in this optimization: additive updates, multiplicative updates, and these swaps in the space of permutation matrices. And I'll just say in each one, what was the biggest extension that we made to sort of try to do this optimization more efficiently. So let me start with additive updates. And how we went beyond line search. So just quickly to recap what Dan covered, right? We have an objective function. We're going to do a first order method. We compute the exact gradient of it for a sparse matrix. And then we take that gradient and project it onto a permutation matrix. And the simplest method is to just do a line search. A method that gets you a little bit now, the bottleneck in this method is running the Hungarian algorithm. So you'd like to do this with as few sort of projections as possible. And one way to do that is to store all the permutation matrices that you've seen so far and replace this by this line search between 2 permutation matrices by a quadratic program that searches within the simplex of, say, the last k permutation matrices that you've come across. And here's just a plot that shows that that quadratic program doesn't have to be very large before you start kind of maxing out. You improve very, very quickly and faster than you would with just running these sort of independent line searches. Now, let me remind you again that these scores are in the space of doubly stochastic matrices, and that's a relaxation. So they're an upper bound on what the score you could obtain by having a permutation matrix. But what's kind of interesting is that even though it's an upper bound, this bound is actually pretty tight, at least when you're getting close to an optimum. So the bound seemed tight to 0.07%, which was about the same order of magnitude as the separation of scores in the final stages of the contest. All right, probably the most, I think, interesting extension that we considered was how to do these things not only on sparse doubly stochastic matrices, but dense doubly stochastic matrices. And for this, we really had to, okay, let me remind you where the bottleneck comes in here. For these multiplicative updates, again, we have this objective function that's quadratic. We can compute the gradient. The element-wise update just takes our current doubly stochastic matrix and multiplies it element-wise by this gradient, and then does some things to normalize it so it becomes doubly stochastic again. But the important thing is that when P is dense, right, the gradient is also dense. And so to compute this sum naively is order n to the 4th, and it's very slow, even for matrices of size 18,000, which can fit into memory. So we wanted to come up with a way to sort of beat that scaling, and here's how we did it. It was kind of a convoluted approach, which I'll try to summarize very quickly. The first thing was to write the minimum of 2 integers. 2 positive integers as an inequality, right? So this is a very simple one. The minimum is upper bounded by the square root of a and b. Note that this bound is exact if either a and b are 0. It's also exact if a equals b, okay? Now, what's interesting about this bound is that if you substitute it into the objective function, you turn something that looks, naively takes order n4th to compute into something that takes order n cubed, okay? Okay. Now, this is still a fairly loose bound, so it's not a very good replacement for the objective function as it stands, but there are ways to refine this bound. For example, if you know that a and b are both not only positive, but greater than some other number c, then you can write down a more refined bound that is exact when a and b are either of them are equal to c, or again, when a is equal to b. Now we're going to exploit the fact that we know that our edge graphs, A and B, that's summarizing the connectomes of these flies.
Can you go back for a second?
Yes.
So you're going to go through contortions to convert your geometric mean back into a min, I'm guessing.
You'll see in a second what we do.
The science question I would like,
Yeah.
I wonder if geometric mean is actually a better objective to optimize.
If it is, then the problem gets even simpler. Yeah,
Okay.
that's good. But the contest was the contest. So yeah, the contest was the contest. That's a very interesting question. There's also lower bounds that you can do besides these upper ones that might also be good surrogates. Okay, so now we're going to exploit the fact that these connectome graphs, that the synapses are all integer valued, and there's only some finite number of values that they obtain, right? So this min actually takes values between like 0 and 600, possible integers. Let's just enumerate all those integers. And what we're going to do is for every interval between successive integers that occur, we're going to define component graphs, okay? And the exact definition of these graphs is not so important. Let's just say that every component graph of the male fly connectome is sparser than its true connectome, and same for the female graph. And you just kind of have to trust me in the short space of this presentation that if you define these component graphs in this way, of which there's 400 sparse component graphs, then you can actually rewrite the exact gradient as a sum of something that does not involve a min. Okay, and if you wanted to get a bound instead of an exact result, you could just not do this for as many graph components as there are unique integer values of the number of synapses. But the important thing is when you write it in this way, you've now changed the order n fourth into something order n cubed, because this is just matrix multiplication, and there's a prefactor there, which is the number of components. But 400 is much smaller than 18,000. Now you've converted this into dense matrix multiplication. This is where we put it on a GPU, and it was about 1 minute now for every multiplicative update.
What is this notation up front with the aij greater than?
That is just indicator function. Yeah, 0 unless that's true, 1 if it is. Thanks for asking. Okay. All right, so that's what we used the GPUs for. Now let me get into this is sort of the most frenetic part of our efforts, which is back in the space of permutation matrices. What Dan talked about is if you got a solution, you can run a check on that solution and find, are there any simple pairwise swaps that could improve your score? And if they are, implement those pairwise swaps and keep rechecking until you can. So that's what I'll indicate by this sort of notation, right? We're going to max over all indices alpha and beta, where we kind of do a swap of the neurons, alpha and beta neurons, before we apply a permutation. That takes about 50 lines of code in MATLAB to compute all those swaps and then to execute which ones are best. So the obvious thing to check is, can you do this for more complicated types of permutations, right? So just writing down, right, here's what 3-cycle would look, cycle through alpha, beta, and gamma neurons. You can do this for pairs of pairwise swaps, okay? You get more lines of code. Pairs of triple swaps, more lines of code. But of course, what you care about here is not how many lines of code, but how long it takes to actually perform these operations. And what you can see right away is, well, there's 18,000 squared pairwise swaps to check, but there's 18,000 cubed cycles to check. And so you're not going to be able to do this exhaustively. But what you can do is do this sort of greedily. So you can say, well, I know I've gotten to a place where no pairwise swaps will improve my score, but I can take, say, all the pairwise swaps that are least malign, least malicious, right? Take some subset of those, let those be the indices of alpha and beta when I check over 3 cycles, and now just optimize over all possible values of gamma, right? And having found some, checked over, if you found that now your solution is robust to all 3-cycle checks, so you can say, well, which 3 cycles were least malicious? Now consider all pairs of these least malicious 3 cycles. And you can, in this way, it doesn't change the number of lines of code really, but you can now scale to higher graph sizes and still check as many higher order swaps as your sort of computational budget allows. And I will just say that in the last week of the contest, when it seemed that the leaderboard was changing every 30 seconds, we were implementing more and more of these cycle checks, just to try to maximize our score as much as we could. Right, so these are the swaps for the final 0.001% improvement, I think, that we found. And the x-axis here just shows which swap led to the improvement. And anytime you see something red on that swap, it means that you would have gotten stuck if you were only using pairwise swaps. And in fact, at the very end of this plot, you see a 5, and that was a 5-cycle swap, and that meant that all pairwise three-way swaps, pairs of three-ways, pairs and triples and quadruples of two-way swaps were already stuck. But the 5-way swap unlocked a potentially higher order solution. Okay. All right, so let me just conclude now. This really was a multi-pronged attack. We came in with one strategy. When it got stuck, we went to many others. I think the key one was going back and forth between these continuous and discrete spaces and really optimizing for the objective function, which was given to us in the contest. The next question, I think, is how you would scale this approach to larger connectomes. The contest was sort of very well organized that an 18,000 by 18,000 matrix is something you can easily fit into memory. We didn't talk about any we didn't try any divide and conquer techniques, but it seems like you would want to use prior knowledge if you were trying to do this for larger graphs. Interestingly, the contest organizers provided a benchmark solution. We were curious if we really needed that benchmark solution. So what this graph shows is starting from the doubly stochastic matrix, which uniformly maps every neuron into every other neuron. So not using any prior knowledge, how quickly could we ramp up to the benchmark? And what this plot shows that in 90 minutes, using the multiplicative updates, the dense ones on the GPU, we were already surpassing the benchmark. So this is interesting because it shows that connectivity alone is probably all you need to optimize. Finally, I have to say that I've never participated in a contest before, and the element of competition really did spur us to try lots of things. For further work in this area, especially given the federal climate for funding today, you might want to try other sorts of incentives. There might be a market here. In all seriousness, let me just say that the contest is over, but obviously the science continues. We're delighted to play some small role at the beginning of this journey, and we're looking forward to future work in this area. So thank you.
Awesome.
What's the size of the memory of your computer?
For the laptop was just what was it?
8 gigabytes or something like that. Laptop RAM.
RAM? Yeah, it's not that big a RAM.
4 or 5.
I think it's more than that. I think mine has like 64.
You have a more expensive.
I have more laptop, but they were working on his laptop too, right? So I have a maxed out PowerBook, whatever Pro or something like that. So
the first part also finished on laptop, right?
Yeah, everything that Dan spoke about was laptop, and the limiting factor when we went to the GPU wasn't memory. It was just fast multiplying of dense matrices.
I'm confused. The multiplicative updates on the laptop?
Sparse.
Or sparse.
I didn't do the dense on the laptop.
Oh, okay.
Yeah.
For your movement function, right? There's this trick in ML. It's called the log sum x trick, right? Where you take the log of the sum of the x of the to get the max, right? We tried sort of like negating that to get the smooth min with that trick instead. Like, would that work?
We did.
You should repeat the question.
Yeah. So okay. So the question was, could you use like the log sum x trick to approximate the min smoothly? I think that would still scale in the same way as the min, but it might give you something more. I don't know, but I don't know.
It's like a soft min.
Yeah, that doesn't actually affect. That would only be applied to the edge weights, not actually to the variables that you're optimizing over in the matrix. So I think it would just change what you were optimizing rather than anything else about our code.
Make sure, as a clarifying question, your Frank-Wolf method, were the matrices dense or sparse throughout? Or
sparse.
Or sparse, and then you have the sparse assignment for doing the Hungarian, or what do you do with the Hungarian part?
Hungarian part would be, we'd used it, in that part to take a sparse doubly stochastic matrix. That's the sum of relatively small number of permutations and then project it back to a permutation matrix.
But use a sparse.
But your solver for Hungarian exploited sparsity or not?
No, so we could have done Frank Wolf on the full dense one. But we didn't actually do it when we were actually working on this problem. But you could easily do it. You could start with the uniform. You'd probably get a very good solution quite quickly in the minute.
Yeah, we have done that.
You see that, right?
But your objective function is a little different. But
Can you go back to that original graph of the stages? Confusion though.
Which
About
the original?
yeah, the first green.
well, the green, well, because it was the original plot.
Yeah,
This one.
this one.
Yeah.
Blue. You're talking about the blue.
Yes, about the
That's right. Yeah, it's for the blue plot. Yeah.
That was all sparse.
It started from the benchmark, so it stayed pretty sparse.
Every Frank Wolf snap goes back to permutation.
But
No, it was just working with the Frank Wolf, but it was keeping it pretty sparse when you find these.
But you had started with the Berry Center as well. That was probably dense code.
That was dense code. Yeah, that was dense code.
We'll make sure wasn't.
This one was starting with the benchmark. It's sparse, and the Frank Wolf just keeps it as a sparse doubly stochastic matrix. If you project back down to permutation, obviously that'll degrade the score, and that's what you see with that drop, essentially.
Yes.
Yeah.
Yes.
I have two scientific questions, but first, in the spirit of the competition, you said that even starting with random initial condition, you took about 90 minutes to beat.
That was using the GPU for that run. Yeah. Yeah, 90 minutes with the GPU to beat the benchmark.
About without the GPU, if you started at a random.
We didn't. I just did this a few days ago to see if it would work, but we didn't start with Frank Wolf. We could try that. I don't know how long that would.
Okay.
Yeah. So we could. I mean, another way of doing it is if you use an approximation like we talked about to the min.
That's true.
And then you could do dense. You could then do it quickly, and then you could actually.
That's true.
With the Berry Center, you're starting with a rank 1 matrix. There are you could still having sparse representation potentially.
But once you apply the gradient,
Yeah.
after one update, I don't think it stays low rank.
No, but I think let's talk afterwards. I think you have a combination of
For the additive case, for the additive updates, yes.
Right, that's right. But not yeah.
Not the multiple.
I'm additive world. Yeah.
That's true. Yeah.
That wasn't my scientific question, but in the spirit of the competition, we used a code written 9 years ago that started with a random solution and beat the benchmark in 70 minutes. But the scientific questions I have are, how would you modify your algorithm if the networks did not have the same number of nodes?
I mean, you just have to consider some rectangular version of a doubly stochastic matrix.
I mean, some constraints then have to be consistent with each other because you have a different rectangular matrix. You can't make them, all sum to one, right? Rows and columns. So you have to think about that. So, you'll have to think about the marginals.
And what if the objective changes? That's my second question.
Well, it depends how it changes. If it's a simple quadratic, then it's even, you don't have to go through some of these contortions. I guess, I guess in fact we didn't even when we were trying various looser bounds on the min, not the equality, but just we had loose upper bounds and loose lower bounds, and using those things could be very fast too, because instead of having 600 components, you would just have one or a dozen components, and that you could run on a laptop too. And I think even starting from the uniform, we were quickly beating the benchmark using those scores as well. So.
Okay, so I think just to make sure we have enough time during the break to eat.
I have one question maybe before we end. It's more of a biology question rather than about the method. So if you assume that there's error in the matrices, so that maybe one data set has poor neural reconstruction or wrong synapses, would you change anything about your approach to find? There is a correct solution, but there's error in the measurement.
I think one of the I thought one of the kind of reasons for using this min score was to try to be more robust to errors in the number of synapses. I think
there's a slide about this actually in the questions.
Okay.
Yeah. So I think that was one of the reasons, but obviously then it makes it harder in some sense in optimization because we have to think carefully about the quadratic function that it represents. So, yeah. So defining the optimization properly is probably the way to handle this kind of robustness here.
All right, congrats.
Thank you.
Great talk. And then
They said start.
did my thing disappear? I want to also quickly mention the other top scorers. So I know it was all that benchmark could be beaten very quickly, but still, if you were able to beat the benchmark, I think it's non-trivial. At least it took to generate the benchmark from scratch.
Oh, I see.
David, Harry, Brigitte, and Lee. I think David is not here for the good reason. Hey, David. He's been inducted to the Computer Science Hall of Fame, so congrats on that. They made a huge effort, and they worked very hard, and they came so close. So very exceptional effort, and we have other souvenirs for the team. We have a 2-pair team because of the financial situation, but we did most of the work, I think. And then the third place is Yusin here online? Yes? Okay, yeah, congrats. Hope to see you guys in person also at some point. And when you come, we'll have a present to you too. Third place was Wayne. Is that right? Yes. Wayne, Marcus, and Russell. Congrats.
Dad doesn't get anything.
Yeah. I wrote the code.
He did. I gotta give it to him.
And we'll be hearing from them in the next session. And last but not least, Team FAQ, John. Right. So I want to quickly address some of the questions that came out through the RSVP form, and I tried to kind of prioritize them based on how many times they showed up. So the first one was about the motivation for this peculiar objective function, and this is also the question referring to the question Mala asked. So maybe I will just spend most of the time on this. So you can basically guess what is the right objective function by looking into the existing similarities of the known isomorphisms in the brain. So in this case, you can select cells in the connectome that are singletons. They only have one cell in each hemisphere, right? So they have only 2 cells per type. And then out of those, there are about half of the cells in the Flywire brain are those. And then from them, you can sample small subsets. You can say 10 cells on left side and on the right side of the same type. And then you expect these subgraphs of size 10 on each side to be isomorphic or almost isomorphic up to reconstruction errors and up to biological differences. So you have now you have some sort of like a ground truth to know what is the right alignment. And then when I kind of evaluated different metric functions, what I did is pretty simple. I just sampled out of these small graphs. I think I selected up to size 12 so that I can go over all the permutations. And then I asked for which metric, and the metrics I tried is this Jacquard metric, the weighted Jacquard metric that was finally chosen. And then L1 and L2. L2 is the most standard one probably, and cosine. And you can ask for which metric you get the highest score for the right alignment, right? And you can repeat it thousands of times and you can get a pretty good confidence. And so from here, conclusion is that while Jacquard was the better predictor, cosine was the worst, and L1 and L2 were kind of in the middle. I think L1 was slightly better than L2.
So what do you mean by cosine?
Cosine similarity.
What's the vector?
So the vector is the adjacency matrix. You look at it as a one-dimensional matrix, as one-dimensional vector, and you can just compute, right? And so what is the reason? The reason I think is related to what Mala mentioned is the noise. What you get in L2 is if you have if you have a big difference between the two data sets, and as you've noticed, there is about 3 times more synapses in the male data set. Then L2 really latches on the biggest difference, right? It kind of it amplifies the biggest difference, while cosine ignores completely magnitudes, right? And so this checkout is somewhere in between. It does give attention both to the set of the partners as well as to magnitude. So this was the logic. In parallel, I think it's also less standard than the other metrics here. So it somewhat made the contest even more a little bit more solutions more general. So if you are able to solve it for this peculiar metric, then probably your solution can be generalized.
To clarify, the WJAC is the function that we optimize.
Right, it's the weighted Jacquard without the normalization. Yeah. So Jacquard is just the intersection over union, and this is just minimums over maximums. There was a couple questions about possible opportunities for community to contribute. Maybe Marissa or Amy would like to answer this.
Well, we need your annotations in the bank. So if you know some neurons and they're not yet labeled, please add the annotations in bank.
What's the right way to reach out?
You can, Amy, as she shared before at her beginning of her talk, includes the requesting early access through the Flywire.ai bank early access request link. And then we'll go through with getting you onboarded so that you can interact with the system to add annotations like cell types.
Yeah, and a lot of these tools, software tools, can be used to really infer cell types without knowing much about biology. So if you're coming from the computer science side. How graph embedding methods are useful in connectomics. So I think in general, the main application would be comparing connectomes. And then comparing circuits within a single connectome. These graph matching type problems are used to do these comparisons based on connectivity. And they are pretty robust, as we've seen in this data challenge as well. Here, there is a little kind of approach we're using today. In fact, this is a work with Mala, Chris, Jay, and others. What we've done with the results of the data challenge, we now have basically the intersecting matching of all the top results. We can construct a consensus between the two data sets, the sets that are always matched together. And then once you have these ground truths of matching from one connectome to another, then you can basically send it to all the other cells just by embedding these other neurons into this feature space where the features are how many. So this is even if you are able to solve this problem on a part of the connectome, it's still useful and gives you a good prediction of matching for the rest of the neurons. There was a question I would like to see. It's a 3-part question. How the data was created. We have plenty of information on Flywire.ai, and there are links to videos, many informative articles were released last year. The video that I would recommend the most is Sebastian's 15-year-old video on TED. It's very good and entertaining. If I remember correctly, it even tells what's the difference between female and male brains.
Okay.
Yeah. What neuroscience knowledge could be added to to make this problem basically easier. And indeed, you can use a lot of the information that we already have and make kind of some sort of like a pruning and more constrained problem that would be smaller and easier to solve. But intentionally, we wanted to we obfuscated all the IDs, all the information about the connectome, and we wanted to see if connections alone can be used to align data sets. And the answer is yes. All right, the challenges with graph matching in the next couple of years, I don't know if it's in a couple of years, but the scale is one challenge. So we'll have larger connectomes coming online. But I think more than scale, also the variety. So these flies, the Drosophila, they have almost identical connectomes between individuals, which made this problem somewhat the easiest setting for comparing connectomes. And it was still not easy, right? Because we had a lot of differences between the two matrices. But if in future we want to compare, say, across a species, then we will need to have methods that are robust enough so that if the connectomes are very different, you can still use this connectivity to align them. So one example could be comparing like a bee connectome to a mosquito connectome, things like that. By the way, if anyone wants to add or answer these questions, please. Empirical evaluation of the alignments. We have reviewed quite a bit, maybe hundreds so far. Chris, is that the case of these aligned neurons?
We're getting up to close to 1,000.
Close to 1,000, and we plan to review all of them. And
1,000 what? 1,000 alignments?
All right. So we took these results from the data challenge, right? And we have these alignments that were made based on connectivity matrices. And now we're reviewing them and comparing them to alignments based on morphology of neurons. And reviewing, okay, in this case, this is better alignment than this, and so on.
A related question, did you say earlier that half of the neurons have a known correct mapping between the male and female brain, or between?
So that was within the same brain. You have half of the neurons, half of the neuron types, they have exactly 2 neurons, which means that one in the left brain, one in the right brain. And so if you sample from this set of the singleton neurons, basically there are unique neurons, one on each side, then you can have a basically known isomorphisms.
But that's between left and right. What about between the individuals?
Between individuals as well. So we don't have many data sets that are full. We have Flywire, which is our own full brain. BANC is being annotated right now, so it's almost there. But we do have a male visual system from Genilia. And so we can compare that with the Flywire, one of the optic lobes in the Flywire. And this we did as well in the past. So these are, again, the same types of neurons, and you can kind of have the same kind of construct from there.
I mean, but one constraint on comparing male and female nervous systems is that we know there are biological differences. There are some neurons that are present in one connectome and not in the other. And so, so there'll always be sort of a confound in these comparisons as we expect to find those differences.
That's one of the ways that the challenge was a bit unrealistic, because they were forcibly made the exact same number of neurons.
That's right. Yeah, we kind of did some data cleaning so that it fits nicely into.
I noticed the ghost node with no connections.
Yeah.
That was a pain in the ass.
Had to find it.
One thing that might be appropriate for your testing is that there are kind of groups of neurons where we see where there are kind of a little bit of invariances where you scramble them a little bit, or you do these pairwise swaps and you don't change the source. And they tend to be kind of low connectivity ones. So, instead of saying that you just have a one-to-one output, you might also have an idea of kind of, well, these groups are kind of mapping.
Right. But this makes it even a little bit more work. But in this case, we have a huge sandbox of like a known isomorphisms. So I kind of went with the kind of most obvious way to do it.
Yeah, but the biological discovery now is we're finding for the first time the complete set of neurons that are different between the male and female nerve cords, which is quite exciting. Nobody has found that complete set before, because this is the first time we have a complete map of both the female nerve cord and the male nerve cord. So,
The question for the winning team, did you try it on other graphs?
Oh, other domains.
I guess, yes.
Problems.
Yeah. Well, we have some preliminary results on embeddings using this method, but that's a future topic.
Okay, future talk. Stay tuned.
Since the data was completely decoupled from the source, and I didn't come from the biology side of things, right?
Yeah.
I looked at the data just agnostic to the source.
Right.
So in theory, I could have tried this with other, whatever we did, I could have tried against other graphs that were non-biological in nature, right?
Yeah, of course, but they have these biological connectome graphs have their own characteristics. Like there are kind of physical graphs. They are in space in 3D, right? So you cannot have arbitrary connections. But you can.
We're talking about that was first invented 9 years ago has been tested on a plethora of networks, like
so
many different types of.
I was just thinking about the application when I go back into my world to think about what I'm learning here, right, for alignments in the technology space, because it seems like there's quite a bit to learn.
Let's let the people eat.
That was my only question, by the way.
It's a fun age. I have the same. Right.
So it's always that. Shh.
I just mentioned to Russell, I wish I will have the same collaboration with my daughter who is starting CS next year at some point.
Yeah.
Yeah. Why are there more female neurons than male neurons? I'm not sure if this is known. Maybe Mala, you know?
They're smarter, right?
I said the opposite. There was more male connections than female connections in terms of magic.
Wise man speaking.
Not true in C. elegans.
Yeah, so there's one part of the data set that is quite enlarged in the female, which controls egg laying and all the reproductive behaviors that males don't do. But there are some neurons in males that control, for example, singing. So males will sing to court the female. Females are not singers. Those neurons are present in males and not females. So yeah.
Another huge difference between the challenge networks was that one of them had many more connections.
Yeah.
Was there what's the reason behind that?
Was the female individual?
I don't think it's due to age because the methods that are used in Janelia for detecting these connections and the thresholding and filtering are different than ours, right? So this is probably the main reason. It's not. I don't think it's a real biological reason.
Methods.
Yeah, unless there's something else known. I'm not sure. I don't think we expect male connectomes to have 3 times as many synapses than females. It's just a reconstruction artifact.
Yeah, I think, right, Sebastian, it's BibSem versus TEM most likely.
Maybe, we don't know. Yeah.
Okay, so just very quickly, a question, what came out from past challenges. And so the conclusion, I will not go into details. We had the past challenge, minimum feedback sort. Data is published, software package with the paper is in the works. There are some interesting findings here. This is a happiness from the winners of the past challenge. Then there was a challenge before on mapping visual cells to columns, and this is as well, data is already published and used in multiple research papers. And now we're working on extension to make it fully automated. This is a joint work with Srijit, who is also working on that project. And I don't know where you have time to do homework at high school, but he's doing amazing work on this as well. So this basically enables us to map cells that are closer to the central brain to columns in the retina, which is pretty amazing. And then this is the also joint work with the winner of the first challenge, David. And next challenge is already online and might be might be the easiest in terms of like a problem statement. All you need to do is find cliques in the brain. Cliques are these fully connected graphs.
Is it the same data set?
No, this is a much larger data set. And this
for this data, for the existing.
Okay. Yeah, so this is much larger. It's like about 6-7 times larger, and it's a full brain from Flywire. But again, here I think all of you are familiar with the max clique problem. It's a notoriously hard problem, but in this case, I do believe there is a way to leverage this, the constraints that the physical connectome has. And indeed, the largest clique that I was able to find is in one region of the brain. And then this is also a unique challenge because all the data is given out. It's not obfuscated, so you're welcome to dig into the data set and use coordinates, annotations, and so on to speed up your algorithms. And it's related to motif search. More information on the page. Please check it out.
If you show me where the data set is, I'll probably have the answer for you tomorrow.
Great. It's just there on the same site. Codex at Flywire. Codex.flywire.ai. There's a link here I should show, but I can send email to all the past participants. And yeah, so this might be your opportunity to get a photo with connectomic celebrities. Yeah. Yeah, and this, I don't know, this might be the last challenge of this form. So we'll rethink what goes after that. The deadline is July 31. Okay, so we'll have a short break, and at 1:30 we'll have talks in this room, but it will be on a different Zoom link for technical reasons. So if you want to stick around online, please go over to the next Zoom link at 1:30. If you are presenting here, also please join this Zoom link and share your screen through Zoom. And we'll have 5 talks. I hope so. Is Kyung-Yeon here? Oh, here. Are you online?
I'm here. Yes. Remotely.
Yeah. Okay, great. So we'll have 5 talks, 5 short talks, and hopefully conclude by 3. So take a break, and there is lunch.
Hi, Malin, yes.